Oh, we got a different. Okay. It's working. This is working. Was that?
Malayalam, I think. Basic South online.
Yep. You're right. Tamil and Kannada is very similar.
Little bit of Malayalam.
Yeah, but the closest is Tamil and Kannada. Yeah. How do you know that?
I studied in Karaikudi.
Oh, but how do you know Kannada though?
Taking Tamil Nadu.
Yeah.
I have seen people speaking in Kannada and I can make little bit of.
Right. Because see, my husband is Kannada, I am Tamil, and I can understand everything in Kannada, and I can speak. Same, it's the same.
But the way they speak, they make out of it what they are.
That is right. Are we waiting for anybody or should we start? Because the online people are all waiting. How many are there? 7. Boss who's coming? Okay. Just wait. Should we start? Okay. So, should I start?
Yes.
Okay. So in this talk, basically, we are going to talk about 2 examples, 2 of the ongoing project. And it gives an example of, the first one is mostly on modeling, developing a simulation model for the power reactor people. So this is again, as we already saw, steam generator units, heat exchange tubes in SG units, and eddy current inspection model. We saw differential probe is one, but there are other kinds of probes. And the second example is for the aerospace industry, where you have multi-layer riveted structures. And eddy current GMR system, that's what I'm going to talk about, and how we use the model and came up with sensor design, instrumentation, and everything. Okay. So this is an example of the nuclear power plant. So this is your primary vessel, and the primary fluid goes into the heat exchange rods, and it keeps circulating. And outside this is the steam and water, high pressure, under high pressure, which the heat is transferred from the primary reactor fluid into the steam, and then that goes and drives the turbines to, and then you have electricity. Okay, the turbines are here. So that is the application that we are looking at. Now, there are a number of types of defects that are created in the in this particular scenario. So as I mentioned earlier, you have, this is the support structure. If you look at this is the case where you have this, the tube, the support, and then there is a lot of crud that is deposited. So the tube itself bends. So there's denting, and then there's cracking in the in the tube support region. Then of course there's always, most of the defects are usually formed close to the support structure, and then there are different types of defects that get that are created. And so we are interested in detecting these types of defects. I mean, that's what the nuclear industry does. They use eddy current probe and detect these defects. Okay, typical steam generator tubes. In any each nuclear power plant can have from 2 to 4 steam generator units. Each of these can have from 5,000 to 20,000 tubes, heat exchange tubes. And the outside diameter can vary from 1/2 inch to 0.875 inch. And the wall thickness is given in inches here. The material is a non-ferromagnetic Inconel, nickel chromium ferrite alloy, and so on. There are different types of grades of Inconel. And the purpose of the steam generator inspection is to first they do a pre-service baseline inspection to detect manufacturing defects. And then, of course, after every operating cycle, they will inspect it and save all this historical data, identify, okay, all this. So that's the procedure that is used. So the typical eddy current probes that are used over here are the bobbin coil. We have seen that, which is very high speed, 40 inches per second. And we saw the disadvantage of bobbin is that it cannot detect circumferential cracks because that is parallel to the current direction. For detection, the current has to intersect the crack. Then they came up with this rotating eddy current probe, which is very slow because it has to go spirally and cover the entire region. So there are something called pancake coils, there is plus point coils, and transmit receive coil. There are different types of coils that are used in this rotating platform and to measure. And then, so this was too slow. So then people came up with the array probe. It's a non-rotating, it just goes straight. And because you have an array of coils, and this is in the transmit receive mode. So there's a single coil transmitting in this array and 2 coils receiving in a differential mode. So it has is sensitive to both axial and circ defects. So these are these are the commercial probe systems that are used in the inspection of steam generator tubes. Okay. So what are the issues in the inspection data? There's noise due to probe wobble. The probe can, when it is going there, it can vibrate. There can be surface imperfections, denting, surface roughness, and so on. There's instrumentation drift that can give rise to different type of signals. The coils themselves cannot, all coils are not the same. They can be imperfect, they can be breakage, and that will give rise to noise and lift-off variations.
Should we do an ND?
Of the coil itself, yeah. So we need to have a self-inspecting coil. Suppose it's possible, right? If suddenly the coil resistance goes to infinity, we know that something is broken completely.
Have you observed this type of phenomena in magnetic flux leakage that sometimes that bit has undergone some flaw itself while taking the collecting data?
Industry has not come to us with that problem. So obviously these are pretty rugged, and there are not moving parts or something that can break. The only thing that is delicate is the array of Hall sensors that they use. And sometimes you'll find dead channels when there'll be one of the Hall in the whole sensor array can die, and you have a black line over there. So you know clearly that there is something and we can replace it. Otherwise, no. So interference, there are geometrical features like the tube sheets, tube support plates, and anti-vibration bars. When you have the U-bend right at this, there are bars that keeps them in place because they can vibrate because of the flow-induced vibration. So these are the things that you need to know. So why do we need? So we got this project to develop a simulation model for steam generator tube inspection. And we've already seen this, the morning, what is the benefit of simulation models? It can predict the signals for any defect geometry, which are not, so that can be used for training the analysts. You can also look at the effect of probe wobble, the frequency, the sludge on the probe measurements. How does it change defect signals? Visualization of field flow interaction, optimization of system design, test bed for generating defect signatures, probability of detection studies. And in reverse engineering models, if you have a complex signal that looks very strange, not something that you've encountered before, you can use the model in reverse engineering to find what is the problem. So the key advantage is that it provides an inexpensive, very fast method to simulate realistic geometries. So how does EPRI use our model that we are developing? The utility engineers use them in complex signal interpretation. That's what I just said. And tube integrity assessments, assist in POD calculation. There are inspection vendors. These vendors are the ones who design probes. So they can use in signal interpretation as well as in site-specific product development. It's more a procedural thing. How does it change from one unit to another unit? Because the steam generator unit design itself can change. And so how do you do that? Then probe developers can use for designing probes and optimizing. NDE instructors can use it as a training tool, and they generate signals for training data. And researchers generate signals for probe technique qualification and signals. So these are the different practical applications that the utility companies are using the model for. Okay, modeling challenges. The mesh size, if the discretization is too, you need a very large mesh to discretize. And that modeling of probe motion in a raster scan, that's a challenge. And that's the one we addressed using the reduced vector potential. These are all non-ferromagnetic, except the support structure is ferromagnetic. Domain discretization is the tube and the region around the tube for any finite element, and mesh size. So it's related. Sometimes when you want a real hairline crack to model that, you need very, very small elements. Mesh size becomes very large. So how to optimize the mesh? Then we have nonlinear material properties in the support region. So all that has to be addressed by the simulation model. So we have very tight cracks. Stress corrosion cracking takes place along the grain boundaries. So it's very, very tight. How do you model it? The way we model it is using a very small element. But we can't just use one small element. You've got to have slowly varying size. So that increases the mesh size. And moving boundaries, this is what I meant by moving the probe when you scan. So you don't want to remesh it each time. So, most people working in the nuclear power industry don't know what's a finite element, sometimes they don't even know the physics of eddy current, okay? So they need a user-friendly software. So you need an interface where they can input define the geometry. And what we have done in our code, because once we know the steam generator design, we already know the inside diameter, outside diameter, wall thickness, and all those things. So we hard code that into our model. Probes are selected using a pull down menu. We have worked with the probe designer. We have all the information so that we can model the probe geometry exactly. And the user then can introduce arbitrary defect shapes. So they can use parametric studies. So how does the signal change with frequency? How does the signal change with conductivity and with a different probe size, all kind of things so that they can do. So this is one of the screenshots. So there are three major the test geometries. This is called the free span. So there is just a tube, that's it. There's nothing. What you're seeing on the outside ring is what they call a foreign object. If a ring has fallen, so it shows that in the free span. This is called the top of tube sheet because at the base of the steam generator unit, it's got some kind of a transition in the diameters. So this is outside and then it enters the inside the steam generator unit. And this is the support region. So if the user want to see how does a defect center of the support, edge of the support, or a deposit in the crevice gap, they can do all that by selecting. The first thing they do is they select the tube geometry and then they can introduce defect. Then they can select the probes. So these are the different probes, the bobbin probe, pancake probe, plus point probe, and array probe. And here are some pictures of the commercial probe geometries. So we know all the dimensions for this. The mesh for these probes are already done and it is stored in the software. So using a pull down menu, they just have to select a particular probe. Then meshing the defect geometry. This is the axisymmetric mesh. This is a circumferential groove. I don't know if they can see that. This is a support structure, tube support geometry with the bobbin probe, cross-sectional view. And you can see that this particular model is fully three-dimensional. So you have here support region, and you can define the defect on the internal diameter, internal to the tube, or on the outside of the tube. All that can be selected. Right now, we are only allowing the orientation to be axial or circumferential or a real crack. So they have some some decommissioned steam generator units. They have these tubes with stress corrosion cracking. They have destructively cut it open and metallographic profile. And that is after they collect the signal, they do that. And then they want, so this is the user interface for real cracks. Okay, so this is an axial, when you have an axial notch they want to introduce, you open up a mesh and then you can hand draw with a cursor, you can draw the profile. Or if you know a profile from which was destructively determined, then we can read it off a file, the depth profile along the axial. This is the axial OD notch on the outside surface. This is on the inside surface. This is a circumferential crack on the inside, on the outside. So all these can be done. So it's very versatile interface that allows them to do a variety of profiles, any arbitrary profile, no limitation. And again, in addition to doing it manually, you can also read the profile from an Excel sheet. Okay, so finally, this is a repetition of what we did this morning. So this is our governing equation in terms of the vector magnetic potential. And this is the Coulomb condition over here. It basically says that the current, there is no divergence of current. Current has to be in closed circle. And so these are the reduced magnetic vector potential formulation, the same equations, we went through it this morning. So this was actually implemented for this particular geometry. And these things. Okay, so this talks about all the details of how we did this, and then the elemental matrix, each matrix as we saw this morning, using the shape function for element by element, you've got to get this matrix, and then you combine them all together and form the global matrix. So this is the right-hand side, how we calculate that. And this is the coil, the source current and the source field. And as I described this morning, we use the Biot-Savart law. And then for any particular probe geometry, we saw the number of probe geometries, you can actually calculate this numerically using Biot-Savart law. Okay, this is again benefits of using the reduced vector potential formulation. Basically, we are decoupling coil geometry from the test geometry. This gives us better convergence, it is faster, it is a lot of benefit. We saw all this just this morning. Okay. So this is basically the validation results. So on this side, you have the experimental data, and the corresponding simulated data is over here. So the way this the experimental system collects data at 4 frequencies at the same time using multiplexing. So for the same defect, you can see how from 50K to 750K, how the signal changes. And we have this corresponding simulated data for the same thing. Okay, so it's matches very well. This is for bobbin, and this is for the absolute, differential bobbin is 2 coils. Absolute bobbin is just a single coil. They measure both. And the reason for that is when you have a very shallow and long defect, the differential coil is very insensitive, because for differential coil, you're calculating derivative. So you want something, a sharp edge. So for such defects, the absolute coil gives better results. Anyway. Right, and in between you have nothing. So here you have, again, for the absolute coil, this is a 40% circumferential flaw. And these are the 4 different frequencies and the corresponding. You can see that the phase of the impedance plot is very, very, and the shape also is very good. One reason is, if you look at the simulated signals, it doesn't open up, it just goes and comes back at the same, along the same path. And the reason for that is the flaw is, when you do simulate it, it's ideal. There is no, if it's a 40%, it's 40% depth, and it goes on. When you machine it, there can be variations. And so when the probe goes past the defect, this side, the front edge is different from the back edge. So you have this kind of you have slightly different opening of this signal. So the impedance traverses this path up to the maximum, and then the return path is not identical. Okay, so that was all bobbin probes, and these are validation of the plus point probe. This is the what they call acquired or experimental data. Now, the experimental data is obtained from a calibration tube, which has multiple flaws machined in it. When we simulate only one flow at a time, right? So this is the 18% internal notch. So this is the simulated signal, and the corresponding signal, experimental signal is over here. So those are the two things that we are comparing, and that is a circ notch on the internal side, and this is the axial notch also on the internal side. At there is a frequency information. These are all screenshots from the software, and it tells what the frequency is. It's at 400 kilohertz, and this is the experimental defect and the corresponding simulated defect. So the match is excellent. They have looked at actual values. They looked at the phase, the magnitude, and the shape and the form. Shape of the signal is very, very. And this is the array probe, the third kind of probe, and this is a 100% axial notch. So it's like a half-inch notch which is through the whole wall. So when I say 100%, it is percentage of the wall thickness. So 100% means it is through the entire thing. And these are the three-dimensional plots of the as I said, in the array probe, it generates what's called as the axial channel and circ channel. And so this is the axial channel signal, and this is the circ channel signal. And the match is very, very good. So this is the top view, and this is the three-dimensional plot of the thing. So that is where we are right now in this particular project. But right now we are also modeling. Every year, what happens is the industry gives us, can you model a foreign object? Can you model a different probe configuration? So we keep adding on to this, and so it's now grown into a really big software. And we have about 4 generations of students who have come in and they work on it, and they leave, they transfer technology to the next batch of students. They work for 2-3 years. So it's been going on for a long time now. And this is still continuing. We already have in place for the next year what the work scope is, what kind of activities we're going to be doing. Okay. So that was one project which is purely on modeling. And the second project I wanted to discuss this afternoon is for the multi-layer geometry for the aircrafts when you have riveted sides. And so what we built for them is using eddy current for excitation and the GMR sensor for measuring directly the induced fields instead of looking at the eddy current pickup coil. Okay, so and this allows us, as I mentioned in the way back then, when you have very low frequency operation, the eddy current signal deteriorates, becomes very noisy, becomes very small. Okay, so this is the project that was given to us. What was the objective was to detect small cracks. If you look at, this is the side view. It's a multi-layer, 3 layers. They are riveted. They are bolted on this side. You have access to only one side, the top, and the geometry has edges. It has subsurface edges. We don't even know, but we want to have a robust set of a sensor that will rapidly scan. So clearly we can't scan one rivet at a time. They want a row of rivets, preferably 2 rows of rivets. So they wanted us to build something that will get signals from 2 rows at the same time, non-contact, so it's very fast. And you also want to be able to detect the second layer and third layer cracks. That means you want a penetration of up to 1/2 inch or more. Okay. So that means we have to have very, very low frequencies. And if it's low frequency, we have to we can't use the eddy current to pick up, we use something else. And in the subsurface layers, we can have corrosion, we can have stress corrosion cracking, and we have fatigue cracking. All of them initiate at the rivet sites. Like you see here, if you remove the rivets, you have the rivet hole and the cracks start developing at this point. So the challenges are that the defects are deep, so very low frequency. Secondly, very often the fastener can be made of steel, in which case the steel will, because the steel is a flux concentrator, high mu, produces a very large signal, but the sensitivity is gone. The small defect signal is completely dominated, wiped out. So we have to have a way of suppressing the rivet signal and enhancing defect signal. And the orientation can be in any way. So we need to be sensitive to all orientation of cracks. So this is our sensor design started from here. I think I showed earlier, Boeing had developed this coil, and this coil is again produces a linear current. And as I said earlier, this is a current. There are two coils over here, and this is the return path for one coil, and the other coil goes like this and returns from here. Okay, so the same current is passing though in both. So you have a uniform region where you have a uniform induced current, uniform field. And also in this uniform area, because it's a planar current, and the field associated is going to be tangential. And the reason is, if you look at this, if you have two coils with the same direction of current, and you look at the direction of the B field, all the normal components get cancelled out, and what remains only is the tangential component. And the nice thing about this single linear current, you have a line of symmetry where the field is zero. Okay, the normal component is zero over here, and we can mount an array of GMR sensors, and we have seen that when there is a rivet, the induced currents will bend, will create a normal component. So the GMR sensor is going to pick up only the normal component. This is a defect-free sensor, and this is the defective sensor. So you will see some kind of asymmetry between the two lobes that we observe. Okay, so this is how a typical signal looks like from a single linear current source. So this is no defect, and this is with the defect. And again, I think this is a steel, one is aluminum. With aluminum, you can get a much more sensitivity, because the rivet signal, when I say aluminum, I'm talking about the rivet itself, or the fastener. When you have a steel fastener, then you have strong defect, but you lose the defect sensitivity and all that. Also over here, this is the orientation of the defect is like this. So you can see a lot of asymmetry between the two. In this and in this case, the defect is vertical or at an angle, and you can see that it is already lost when it is, particularly when it is vertical, it's in the dead zone, and you cannot pick up that particular thing. So what we did was, why not have, and like we did in the magnetooptic case, we'll have two coils which are orthogonal, and we'll also have a 90-degree phase difference between X and Y coils. So when you look at the vector sum, you have a current that rotates, okay, circle along the thing. So when you do that, then I will have sensitivity to all orientation. If you look at this is no defect, X in the 45 degree, 0 degree, 45, and 90. So it has sensitivity to all orientation of defect, but there's only one single point symmetry. That means I have only one point over here where I can mount a GMR sensor. Okay. So we looked at, okay, if suppose I still have an array of sensor, what would happen is what would happen is, suppose it's an array in this direction along the red coil. So the blue coil is going to produce some kind of a background field depending on where it is It is symmetric with respect to the red coil. Blue coil is in this direction, right? Can you see the blue coil? Hey, the lights, maybe you can switch off the lights here, then you can see. So this is the red coil. That means current is in this direction. But you have another coil in the other direction. So even if it is static, if I have an array of sensors along this, there will be a different signal along the vertical axis. So this background field is larger than a defect field, so you're going to lose any defect information. Okay. So what we did is, why not have a differential arrangement? So we decided to go with two arrays. We have a GMR array above the coil and an array below the coil. Okay. So we can do a differential measurement. So what happens is, the coil below is more sensitive to the defect. Will have more information from the defect. The coil above will also have some information from the defect, but it has more information about this background signal, the unwanted background signal. So when you have this and you take a point by point subtraction between these two arrays, I can get rid of that background noise that I saw and enhance defect signal. But all this means that we need to do a little bit more instrumentation, because the whole thing was, we fabricated the GMR array. One of our postdocs has a company that does this fabrication. So he gave he did the fabrication of the GMR array. We did all the coil fabrication and the instrumentation of the differential array measurement. Okay, so so that was the I don't have all the complete PCB that was designed for the instrumentation, but I probably have it somewhere in my computer. I can show if you're interested. Okay, the next thing was, okay, we have this basic system, but we needed to do some kind of optimization. So let's look at what we used. We developed a model for this particular coil geometry and the multi-layers and all those things, where we could actually calculate what the background field should be. And, so this gave a lot of guidance as to how the instrumentation should be done. Okay. Because we were operating at very, very low frequencies, like 200 hertz. That's what is applied to each of the coil with a phase difference. Okay, what else is there here? So this shows a schematic. You have, this is a 1/4 inch, this is a 1/4 inch aluminum layer, this is the steel, and this is our two arrays, and this is the excitation coil. That's the schematic of the overall thing. And this was some of the simulation signals that we got. Okay. So we looked at the GMR array from the bottom layer, and this is, we simulated what the GMR measurement is at the top layer, and then we looked at the differential image, and so this is what we get, and then there is a baseline subtraction that we had to do for the edge effects. And once we do that, we were able to get a nice rotating field signal, which is very similar to what we did in the simulation, what I showed. Okay, so this is so this was well, this was still simulation, but this helped us design the differential array. So this is what in the differential array, this is what the two arrays would measure. The two arrays, one at the top and one at the bottom. Okay, so by modeling this geometry exactly, we were able to individually predict the GMR measurements in the two arrays, and then do the subtraction and all that. So then it's in the experimental system, everything is done in hardware, of course. But this helped us get an understanding as to what kind of fields, that's the whole purpose of the simulation model. So these are the simulation results for different orientation of defect. This is like 60-degree defect, this is no defect, this is 30-degree defect, and this is 90-degree defect. Okay. So these are simulation results, and so we were sort of confident we can get this in experimental system. We can instrument it. Okay, the next thing was designing that, we just talked about a linear array line, multi-line coil, which were all uniform, right? Now, one of the things that we wanted to do, so this is this, and if you look at the B field, the induced field in the sample with the uniform coils, it looks something like this. Now, when we do, so that if we want to scan 2 rows at the same time, those 2 rows are going to be somewhere here and here. So it's not going to be get the maximum performance. Whereas, so what we wanted is something where the induced field or the induced current is going to be flat over this region of the coil. If you use a uniform multi-line coil, it's like a parabolic, induction thing. So how do I get a flat region? So what we did is, instead of having a uniform coil, we designed a non-uniform coil. Okay, so towards the center there were more lines, and then these lines were not equally spaced. So we did some modeling studies. So the green line is what you would get for an uniform coil for the induced field. And for some, we looked at one particular case of an optimized of a coil design where we could actually spread it out a little bit. Ultimately, we want to spread it out in this fashion. So the coil need not be uniform, but the field induced has to be uniform. Okay. So this is some of the simulation results. So with a non-uniform coil, we saw this is for the uniform coil, and this is for the non-uniform coil, the induced current. So we did a lot of optimization studies over here to get something better. So in order to help us with this, again, we looked at if the rivet is right at the center, you get a nice, and there is no defect, you will get this. Okay, and this is what we got with the experiment. And when there is no defect, even the optimized coil gives you very similar results. But when the rivet itself is off center, it's 15 millimeters from the center, because if I have to accommodate 2 rows, it will not be at the center. So you have, this is the signal that you have. Well, it is very difficult to see. This is the simulation results, and this is for the optimized coil, that is non-uniform coil. This is more circular than for a uniform coil, which is off-center. Does it make sense? This is the uniform coil. This is optimized non-uniform coil. But when everything is at the center, there is no difference. But when the rivet is at a corner, at the edge, the non-optimized or the non-uniform coil gives us a better result. So that means if there is a defect in that rivet, this will have better sensitivity. Okay, what happened to this thing? Okay, looks like I'm missing some flash slides. This looks like the last slide I have over here. So basically, okay, I think I'm going to stop here. I had a lot of other slides on the actual experimental system and on the signal processing part, how we got the. If you give me some time, let me search for it, and we have time anyway, so I'll do that, okay? This looks like. I had this thing. Should be in this. Sparse coding. Ah. is not here. So let me log into my office computer. See if it's there sitting somewhere in my email. This is draft, okay. Slides for telecom. See, this is the one. I had a whole part of the signal processing of this. This is it's a very interesting thing. But presented it somewhere. Huh. Gosh, it takes forever. Any question on the online people in the meantime? This thing is opening. Yep. Yeah. We're talking about hairline cracks. Yeah. I need to, probably one thing is what we are really simulating is not, it's not a, if a real crack will be touching, there'll be points where it will probably touch, right? When it's very, very, very thin, there is a limitation about the smallest size element I can have, which, and what we are really, that there's a lot of discussion about a real crack and a notch. What we are really doing, the depth profile is different, but the width is constant in the simulation model. Whereas in a real situation, you're absolutely right that it's a real hairline crack is different from what we are simulating. But that's the best we can do. But there are other modeling approaches where instead of using a notch, a rectangular notch, you can just model it by number of nodes and apply an interface condition that the current cannot pass through. So that can be done. But this thing, it's very difficult to change a software that's already been done and developed and so on. But you're right, for this model, this software that I showed does not really do, it does an arbitrary depth profile, but not, the width is constant. But that's a more challenging thing. I'm just trying to see whether Is it here in this? Ah, okay. So let me just use this was actually, you know, I was talking about there was a initiative last year. This was again by the Indian government. It was called Vaibhav. I don't remember what it stands for, but it was mainly focusing on aging aircraft problems. So they had people from all over the world working on aging aircraft to share their experiences. So I just presented this thing, the same problem. So so this basically shows our, I don't know whether you can see the full experimental set, you know, the thing over there that we put together. These are the simulation results. Oh, better. I can't see anything better here either. Yeah, this blue colored thing that you see here, over here, all are the probe and all the electronics, everything was packaged inside this. And this is what we delivered to Boeing. And what you have here is an actual aircraft part that Boeing brought, okay? And we did a similar, oh, it's not here. Oh man, this is just a, oh yeah, it's over here, okay. So this particular one is not, the signal that you're seeing here is from a calibration sample. And these are experimental results from 2 rows of rivets, okay? And this is, okay, this is the actual sample. It had 2 rows of rivets in the second layer. This is about 1/4 inch thick first layer. And you have here a connecting crack. And then you have cracks in this direction over here. I don't know whether you can see that. Over here. And then there are cracks in the horizontal direction. There are 3 of them. This is a very, very small crack, have all the actual dimensions described somewhere. And so this is the, okay, this is the signal at 100 hertz, okay? You know, I talked about steel rivets. When you have steel rivets, you have a very strong rivet signal, okay? And very small defect signal. So how did we suppress the rivet signal? We did 2 frequencies. So our system operates at 2 frequencies, 100 hertz and 1000 hertz. So at 1000 hertz, you cannot see any of the defect. They all look absolutely symmetric. And that's because at 1000 hertz, you only pick up the rivet signal. There is some defect signal, but you only pick up rivet signal here. Whereas in the 100 hertz signal, you can see that there are, where you have a connecting crack, you can see the, you know, it's not totally symmetric, the signal. So all the defect information are there in this thing. So then what we do is we sort of, we have to do some kind of transformation and subtract out the 1000 hertz signal. And this is the residual signal. So the residual signal, of course, this is sort of flipped. This is the connecting crack. And these are these 5 signals, these 5 rivets with cracks in it. Oh, okay. I can use the mouse. Oh, how is it? Okay. So this is the 100 hertz and 100 hertz and 1000 hertz. These are the cracks over here. You have 1 and you have 3 here, and there are 2 here. Okay. And there is 1 more over here. Okay, so we took these 2 and you combine them in such a way that the rivet signals are subtracted out, and only and all this is done, can be done in hardware. So out comes this image, which shows this is this connecting crack, and this little one is also shown over here. And these 5 rivets are these 5 rivets. So the residual, you can see that in these, everything is subtracted out. But basically only the defect signals remain. So this was something that we put together for Boeing and the Air Force. this particular one is all aluminum. It's all aluminum.
The material which you're trying to by using rivet,
All aluminum.
including the rivets.
Including the rivet can be either aluminum or titanium or steel. The rivets are typically, strong materials.
Rest of the material.
But that's how the probe works, right? The probe picks up this normal component. This is like, where I described how the probe works. This is specifically designed for picking up rivet signals. Let me go back to that thing. Okay. So if you look at, it's not what I want. Did I? Okay. If you look at how the probe works, why it's like this, right? So when there is no struct defects, the rest of the aluminum, everything is in the linear region. All the fields are tangential. There's no normal component. Normal components are created by the rivets when the field bends down and it produces a normal component. And that is why, where did I close that? Okay. That's why we only pick up the rivet signals. Because the rivet produces a discontinuity. Wherever there's a rivet, there is a hole and then there's a rivet material. So there is some air around it. Okay, so it's a discontinuity. Yeah. Okay, now I understand your question. It's all, I know, it's all aluminum, but sometimes they can be steel or sometimes it can be titanium too, in which case clearly the difference material, but even when it's aluminum, it produces. Because there is a small, very thin air gap. Okay, now let me go back to that, this one. So, okay, this is the validation on real structures. So what you see here is an X-ray of this aircraft part. Okay, let me do this, and let me go to my cursor. Okay, so this is actually an X-ray, and the X-ray basically gives us a ground truth. And you can see that wherever you have a dark circle, those are steel rivets. And these are aluminum rivets in between. You can't, so when you take an X-ray image, it will not tell you the difference between this rivet and the host metal. Whereas when you have steel, you have these things. So that was the thing. In the field, we don't even know what the rivet material is. So these this is the signal from our system. And you can see that, let me see, wherever you have, the red circles are correct detections. So wherever you see a red circle, there was actually a defect over there. If you come closer and see, you can see in the X-ray image too. Yellow circles are all false calls. Okay. But these are detected, and the red arrows are where we missed some defect. Now this misses, and we're all because we sort of fixed the threshold values that we were going to use based on our lab sample. So if you have a calibration sample of the actual material, we can probably make the performance better. Also, we are using the same threshold whether it is steel or whether it is aluminum. And because of that, we may be missing some of the aluminum rivet defects. Okay, so there are, this is the thing. So this is one particular thing, and here was another one. So there was a 1/2 inch top layer. The sample was 1/2 inch of metal below that, and this is a 1/4 inch top layer. Okay, and the defects are in the second layer. And we can see that there are all of the defects were detected. There were 2 misses, very, very small defect. but the false calls were reduced to just 2. So the performance, I think, the first time go to the actual aircraft and make some measurements, and with not totally blind, it was very good. So this is what one thing that I wanted to also show, but I didn't have. So those are 2 examples of the projects where we use the simulation model to design optimized design of sensors. You may think what is there to optimize in a just multi-line coil, but we were able to see that given this particular condition where you want 2 rows to be done at the same time, we were able to use the model to give us a better design for the coil. No, we have our own code. We have our own, I think maybe for some of the reasons, some of the simulations we may have used COMSOL, but for this geometry, we have one of the student thesis where our own code has been there, and it's more easy to, vary different things in our own homegrown code than COMSOL. So we just, but definitely it can be done with COMSOL. I mean, everything we can do with COMSOL if you know how to use COMSOL. So those are the 2 examples I just thought I'll talk about. I don't have anything else. Are there any questions there? Or?
How did you model the GMR?
Well, GMR, we have the characteristics. Okay, when I talked about on the eddy current lecture, the characteristics of the field to voltage is known, or or resistance, not voltage. Oh, well, voltage, resistance, everything. What we measure is a function of the resistance of that. We can directly convert the resistance into field. So that's what. So that is known for any particular GMR sensor. We know what that is. What is? Well, the VIBO program was by the, don't remember what it stands for. You can Google and find out. Yeah, it was an aging to discuss what different countries do for aging aircraft inspection. So that's what it, VNIT, I don't know what it means, what it stands for. Oh, no, I think it was just the government of India thing. And I think there were other governments too in it. I need to look at Krishnan's email. I would know. What is this? Soon. Okay. This was in 2020, I think. Oh, Vaibhav Summit. Got to see his first email where it talked about.
Vaishnav Bharatiya VNIT Summit. Inaugurated by Ravish from October 2020.
Yeah. What does it stand for?
stands for VAI stands for Vaishvik,
Uh,
VHA for Bharati,
oh,
the
okay,
next V stands for Vaigyanik.
okay. Yeah, so there were people from Australia, Singapore, Germany, USA, and everybody else from India. Yeah. Okay. Should write it down somewhere. Yeah, but this was students felt there were 5 PhDs that came out of this one project. Yeah, it was, for getting $4 million for one group was quite, and that's one of the projects which allowed me to buy equipment because there was enough money for that. Yeah. So yeah, I had one full paper on this signal processing method, and where we looked at various algorithms to suppress it. So I thought I had more. Okay, so that brings this part one of this course to conclusion.
Hello. So any questions from the online participants? And Nima, any questions? Yeah, Nima, any questions? Nikhil? They have sent any chat? Okay, okay then. So we'll wind up now. Okay then, I'll stop sharing. Thank you, Nima, and I'll just take it. Nima, Harshad, Nikhil, Poonam, Rajesh. Yeah, thank you all. Yeah.
So where are they all from?
Nima is, I think Nikhil is in. He was doing PhD from university. I don't remember that name, but Nima was doing from Kerala University. QSET is there.
Pardon?
QSET, Central University,
Chris.
Cochin University. Yeah, so she's from there. She's working in the same domain. And Nikhil,
He works for ISRO or the university?
she's doing PhD, I think. Hello, Nima, you there?
Yes, sir.
Yeah, ma'am wants to talk to you. What you are doing right now?
So
Ma'am,
yeah,
ma'am,
so what?
I am a research scholar from Kochi University.
Yes.
My research area is metasurface, but we have MTech students here. They are doing project in NDE.
Okay. Okay, so do you work with ISRO or?
No,
No, it's just a project.
yeah,
Okay.
just a project.
Okay, very good. I hope the whole course was useful for you.
Yes, ma'am. It was very useful.
Good to hear. Is there others? Can you talk?
Yeah, Nikhil.
Unmute and say a little bit about your interest.
I'll take a peek back. Nikhil?
Mute.
Uh, Nikhil?
Yes, sir.
Yeah.
Yeah, I'm doing my PhD in this NDE for composites, fiber metal laminates.
Okay. Okay.
Which university?
Which university?
I'm in Shivaji University, Kolhapur.
Kolhapur.
Shivaji University, Kolhapur.
Okay. Oh, okay. Very good. Hope this course was useful in some ways.
Yeah, ma'am.
Good to hear.
Thank you.
What's next? Shivaji University, Kolhapur. Study in MIT, Pune.
Okay, so is that all? So we'll stop sharing. Thank you all the online participants. Yeah.